And you should see the record button go up. Okay, good. So well, let me start with just a little bit of the basics here of what we learned about histograms and about normal distributions in the last week or so. So let me, if I were to draw a histogram of a normally distributed variable, I'm going to assume for the moment that student weights are normally distributed. They may or may not be. Let's assume for the moment that they're normally distributed. If I were to draw a histogram, if I knew, for instance, that the average weight, mu is population variable, right, or a parameter, that the average weight for all students in CUNY is 150 pounds, and the standard deviation, the spread of all of those weights is, say, 20 pounds, I might, if I were to draw that as a histogram, it might look something like this. For instance, I might break it up into groups of 10 pounds. So, or let's say 20 pounds. So from 100 to 120 pounds would be one bar, and from 120 to 140 would be another bar, and from 140 to 160 would be another, and 170, actually 100, 100 what's that? Oh, yeah, let me get that out of the way. Thanks for warning me about that. Good. Okay, that's going to make it a little easier to see. So I'm going to redraw this again. I'll go back over this. So if I were to draw this as an omograph, let me see if I can't get rid of all that stuff. Okay, good. So actually, I'm going to do it a little bit differently. Let's say that one bar represents the 120s, 130s, 140s, 150, 160s, 70, 180, just a rough idea. I would expect that most people are going to be around the average. That's usually what you would expect. So I'm going to have a pretty tall bar there for my histogram. So as I get the quantity of people that I would expect to be a little overweight, it's probably not as much as the group that are in that average group of 10 pounds, around 150 pounds, say 145 to 155. And I expect the same outcome for those that are a little bit under 150 pounds. Now, as I got to higher weights, I would expect fewer people in each of those groups and lower weights. And as we moved over and we got to very thin people and very heavy people, I would expect to have a smaller number of those people in population. So in general, when I have a variable that I expect to be normally distributed, I expect the most common outcomes to be somewhere around the middle, with the number of people or number of subjects that satisfy that criteria diminishing as we go further and further away from the mean, the average value. So that takes on a kind of characteristic shape, this kind of bell-shaped curve that we hear so much about. That's a normal distribution. That's really based on chance. What is the likelihood of having someone, if you pick them at random, being heavier than 150 pounds or less than 150 pounds? And what's the likelihood of them being 120 pounds? So this line can represent the actual population, the number of people, right? Or all these different weights, kind of a histogram. Or it also can represent a probability of having a certain weight. So in other words, this whole normal distribution, this whole curve, could represent 100% of the population, right? And if I took the mean to be the middle, and if it's a perfect normal distribution, one of the characteristics is that the mean median exactly in the middle, and it's symmetrical. Both sides are exactly the same shape. So if I were to ask you what percentage of the people in this population would I expect to be less than 150 pounds, you would say 50% of the population. What percentage would you expect to be more than 150 pounds? You'd say 50% of the population, right? If this were 1,000 people represented here, you would expect 500 below the mean, 500 of them to be above the mean. Same kind of deal. You can look at this distribution either way. We're mostly going to be looking at it as probabilities because that's the way it's going to be most useful to us. Okay, so I'm going to open up a document that we have in here that that's on Blackboard. It's a kind of a lab exercise for tonight. And the first thing that we're going to see when we open it up is going to be this representation of the normal distribution using something called the empirical rule. Okay, so if I look at my normal distribution, you'll notice that instead of putting an actual value here, I just put mu for the mean. Right? So instead of 150, it's just mu. If I look to the left of the mean, I could be looking at the number of standard deviations to the left, the number of standard deviations to the right. But just as I looked at before, the probability or the number of people that in this population that are above the mean is 34.1, 13.6. If I add all these together, it adds up to 50%. If I add up the percentage of all the people below the mean, it adds up to 50%. So this represents 100% of the population. So, but I have other advantages here. This shape actually is determined by probability and by a formula. It is actually a formula that represents the normal distribution. Here it is, pretty nasty looking formula. Okay, and what do we have in here? We have the standard deviation, we have pi and e, which are constant. We have x, any particular value for a person in that population, and we have the mean and the standard deviation. So we have the mean and the standard deviation, really what determines the shape of this distribution, how spread out it is, and so on. And so this formula actually represents the line that represents this normal distribution. Well, since all normal distributions have these common properties, they're all going to give me, if they're truly normal distributions, they're all going to give me some way to measure how the population is distributed. Like, for instance, a normal distribution, 68% of the population is between one standard deviation below the mean and one standard deviation above the mean. And 95% of the population is approximately two standard deviations below the mean, two standard deviations above the mean. And if I go as far as three standard deviations away from the mean, I will have 99.7% of that population captured between that range. Now notice I'm only talking about mu, the mean, and sigma, the standard deviation. I'm not using this yet to generalize it to a specific case or to go from this general condition to a specific case. But I will be. I'm going to be taking advantage of our knowledge of the way this bell curve is shaped and the areas in it to make predictions about populations and samples as we move on. Okay, so for instance, first thing I'm going to say is, okay, I'm going to say, let's say we have a normal distribution, heights or normal distribution. Assume the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches. Find the probability that a randomly chosen individual from that population has a height greater than 68 inches. I don't even have to draw anything for that, right? The mean is 68 inches. Probability that you would randomly pick someone from that population that's over 68 inches is 50%, right? Okay, because chances of being above the mean is 50%. Okay, so between 64 and 72 inches. Well, for that, I'm going to actually sketch something. Okay, let me move this out of the way. Okay, I'm going to draw a normal distribution, or kind of a normal distribution. Okay, and what did I say the mean was for the heights? 68 inches, right? Right, that's mu. And what did I say standard deviation was? 4 inches. Okay, so what value represents one standard deviation below the mean? That would be someone that's 64 inches tall. And one standard deviation above the mean, 60 would be 72 inches. And two standard deviations below would be 60 inches. And two standard deviations above would be 76 inches. Well, what does that tell me? If I look at my standard normal distribution, my empirical formula, oops, now let me move it. What does that tell me? That tells me, let's see, 95% below, and okay, I can figure this out. That tells me that between one standard deviation below the mean and one standard deviation above the mean is 60, what was it, 68%? I'm gonna just round it off to 68%. 68% of the population is between 64 inches tall and 72 inches tall, right? So if it's symmetrical, the area between the mean and one standard deviation below is equal to the area between the mean and one standard deviation above. So both of these are 34%. So let me go back to my question. My question was, find the probability that a randomly chosen individual is between 64 and 72 inches. Well, 64 and 72 inches, one standard deviation, what's the percentage there? 68%. That's the probability that a randomly chosen person would be in that range. How about between 60 and 76 inches? Let's see. 60 and 76, that would be 95% of the population. Okay, pretty simple, right? But think of the power that gives us now. Now, based on the standard deviation and the mean of the population, we can make all sorts of predictions about probability of choosing individuals, the size of the population within a certain range, and so on and so forth. So let's move on from there. Assume that the heights of adult Caucasian women have a mean of 63 inches and a standard deviation of 3 inches. What percentage of women in this population have a mean height greater than 63 inches? 50%? Okay, greater than 66 inches. Uh-oh. I drew a curveball there, right? Okay, let's sketch another one here. Whoops. Okay, let me draw a new normal distribution. Notice the shape is the same, but the dimensions are different. Now the mean is 63 inches, right? Mean equals 63 inches. And the standard deviation, sigma, again, population, is equal to, what was it, 3 inches? And so what did I ask about? I asked about the probability that we would randomly select someone, or the percentage of the population that's greater than 66 inches. Okay, so here's 66 inches. How many standard deviations above the mean is 66 inches? One standard deviation, okay. That's equal to 1. So the area here, what did we say the area there was going to be? Remember, if one below was 64, so this is 34%, right? So what's the area below the mean? 50%. So what percentage of the population is above 66 inches tall? What's left? Right? 50, 34, right? Is 84. So that's going to be about 16% of the population is above 66 inches tall. Okay, next question was going to be less than 60 inches tall. Okay, less than 60 inches tall. Similarly, this would be 34% because 60 inches is one standard deviation below the mean. So this also would be 16%. Okay, what percentage of the population of these women is either below 60 inches or above 66 inches? 32, right? 16% plus 16%. Okay, so again, we're using this knowledge to find out more, to understand more and more about this population. Gestation period for humans has a mean of 266 days and a standard deviation of 25 days. What percentage of pregnancies would you expect to be greater than 291? Well, I'm starting to throw a few curves here. So let's okay, you guys online are working on it also. 16%, 32%. Thank you. Good. Okay, so let's draw this standard normal distribution. Oops, wrong direction. Okay, so in this case, let me do this. So my normal distribution is going to look something like that. It's not quite as good as the others I drew. Okay, so the mean is 266 days. Standard deviation is 25 days. And keep in mind now, as we do this, if our distribution looks like this, or if our distribution looks like this, it really doesn't matter. Because the spread, if it's a normal distribution, it's symmetrical about the mean, the spread really doesn't matter the standard deviation makes up for that spread. So these relationships hold true for this distribution, and for this distribution. It's just they have their own individual means and standard deviations. So first thing I want to know, greater than 291 days, so 266. So how many standard deviations above is 291? Well, now one of the things I can do here to calculate this number of standard deviations is to say, well, I'm going to go up here, 291. How many standard deviations? Well, let's see, 291 minus 266, that's the difference, divided by the standard deviation, which is 25. And what does that come out to? That comes out to 25 over 25, or 1. Right? So if it's a little bit harder, if the math's a little bit harder, you can actually use a formula like this. And actually what this formula is x, the value that you're comparing it to, 291, minus the mean over the standard deviation. You might remember this formula from the lecture. That's the value for the z-score. That's what I was saying. You can kind of look at the z-score as the number of standard deviations above or below the mean. So the z-score for 290, value of 291 is equal to 1. So what's the probability of having a pregnancy greater than 291 days? Well, it looks like it's going to be, I think we said 16%, right? 34%, 50%, leaves 16%. You may know that gestation period is not really normally distributed, right? Because you get a lot of premature babies. So it's really a skewed distribution, but we're making believe that it's a normal distribution. So what's the next question there? Next question is less than 241 days. So I'm going to use that Z formula again, is equal to 241 minus 266 divided by 25. This time it's a negative number, right? Negative 25 over 25 is negative 1. So the z-score here is a z-score of negative 1. Z-scores are negative if they're to the left of the mean, and they're positive if they're to the right of the mean, right? That's really by convention. That's all that means. So again, that would be 16% of the population would be below 241 days if it were really normally distributed. How about less than 241 or greater than 291? Well, again, it's 16% plus 16%. 32%. Okay, you guys online are doing that? You could use the Z. Actually, we did use the z-score. The z-score is just another way of saying the number of standard deviations. So yeah, absolutely. Oh, good. And if you guys want to answer each other, that's even better because you won't have to wait for me to notice it. You were about to do that right now. Somebody got ahead of me here. Exactly. Okay, so now let's take a look now at another distribution. Okay, let's assume that the heights of U.S. women have a mean of 63 inches and a standard deviation of 2 inches. What percentage of women would you expect to have a mean height less than 63 inches? 50%, right? What percentage of women would you expect to have a mean height less than 62 inches? Oh, I'm going to have to draw this to understand what's going on here. Okay, let me go ahead and do this. Okay, I'm going to go over here and choose this. Okay, so I'm going to draw this normal distribution. And I said the average height was 63 inches, except this time the standard deviation is equal to 2. Question was, okay, what percentage is less than 63 inches? Easy enough, it was just 50% because that's the mean. Less than 62 inches. What percentage of women are less than 62 inches tall in this normally distributed, this population of normally distributed heights? What's our z-score? Z-score is equal to 62 minus 63 divided by the standard deviation, which is equal to 2, and that's equal to negative 1/2. In other words, negative 0.5. I got a problem. My empirical formula only works for even numbers, like integer numbers of standard deviations. I need another way to figure out what this area. Well, now, because these, based on standard deviation and means, mu and sigma, the z-scores, the area represented by the z-scores, the number of standard deviations, is true no matter what the shape is and what the spread is for any of these normal distribution. So we could take, if we wanted to, and they've done this for us, we could take a distribution and I'll say, I'm going to call the mean of this distribution 0. And I'm going to call the standard deviation 1. So 1 is 1 standard deviation above the mean. 2 is 2 standard deviations above the mean. 3 and -1 and -2 and -3 are, so I'm going to take this standard normal distribution. You heard that word from the lecture. I'm going to take this calculated distribution and I'm going to create a table from it. So which will let me calculate if I were looking at, instead of 1 standard deviation below the mean, 1.31 standard deviation, 1.13 standard deviations below the mean, -1.31, that's z-score. What area does that represent in this distribution? I'm going to create a table that does that. And if you look on Blackboard, or if you look in you obviously in your textbook also, you'll notice that we have a table of z-scores. I'm going to pick one up right here that's from another textbook. I think the one in your textbook is pretty similar. And you'll notice that there's columns and rows of numbers here. And you'll notice that they start at -3.4. That's the z-scores in this column. -3.4 goes to 0, -0, and then 0 picks up here and goes through all the positive numbers. This represents the z-scores. Notice that when I'm looking at negative z-scores, I'm looking at areas below the mean. In other words, the areas that this table is giving us represents the area from that, whatever that z-score is, the value for that z-score, to the left of that z-score, right? So if I had a z-score of -1, and I wanted to know what percentage of the population is above a z-score of -1, I would be able to tell what the area is below -1, but then I'd have to subtract it from 1 to get the area above 1, above that value, right? So this area, this part of the table is all the negative z numbers. And when I get to 50% z-score, when I get to the mean, it's 50% is below the mean, right? You can see it right there, 50%. And this area represents the areas to the right of the mean. So all of these represent values that are above 50%, right? And they shade it for you, so you know this table. If you look up the z-score here, it represents the area to the left of what that z-score is. And since you're to the right of the mean, they're all going to be above 50%. Okay, so let's take a look at how I'm going to use this. Okay, so now I'm going to look up a z-score for -0.5. Is what we're after. Well, the way this table works is it gives you 3 significant digits for the z-score. In other words, if I had a z-score of 2.21, I could look up the z-score -2.21. I could look up the z-score for -2.2, and it would be 0.139. But then if I wanted the z-score for -2.24, if you notice, I have the third significant digit is up here on the top, 0, 1, 2, 3, 4. So if I wanted -2.24, I would go -2.2. Oh, is that value? 1, 2, 3, 4. So the area that's represented by -2.24 is 1.125% of the distribution is to the left of that value. What was our z-score? 0.5. 0.5. What's the third digit? 0, right? So what is the area to the right of that? 30.85%. So if I go back here, the area to the right of 62, or a z-score of 0.05, is going to be 0.3085, or roughly 31%. Okay, 30.85% or 30.31, roughly 31%. If I had asked you what percentage of this population has a height above 62 inches, what would it be? It would be 1 minus 0.3085. Okay, everybody comfortable? Everybody comfortable with that online too? Yes? Okay, we're okay with that. Okay, let's take a look at the next one. So we can use this z-table as a way to calculate all the areas that we want here. We can also use Excel. I'll show you that in a second. Okay, so greater than 66 inches. Okay, we're 66 inches here now. Okay, 66 inches is here. Okay, and what's the z-score for 66 inches? X minus mu over sigma is 66 minus 63 over 2 is going to be equal to 1.50, right? Z-score of positive 1.50. And the problem asks us for what area? It asks us for the area greater than 66 inches. Okay, so if we use this table, first of all, we're to the right of the mean, so we're going to use the positive numbers. So 1.50 represents the area to the left of that represents 1.50. Where is it? Here it is. 93.32% of the population. That's 93.32 or 0.9332 of the population. What percentage of the population is above that value? Well, that area is going to be represented by 1 minus 0.9332 or 0.0768. Did I get that right? That adds up to carry to 1, up 6.668, or about 6.6%, a little under 7%. Okay. Oh, thanks for the help online too. Okay, so that's how we're going to use this. I mean, this is a valuable tool for us now. It's going to get more valuable as we move on. Okay, so body temperature of adults has a mean of 98.6 degrees Fahrenheit and a standard deviation of 0.6 of a degree Fahrenheit. Find the probability that a randomly selected individual has a mean body temperature greater than 99 degrees, less than 98 degrees, less than 98 degrees, or greater than 99. I'm going to go right to D, between 98 and 99 degrees. Okay, let's just tackle that problem. Okay, I'm going to go over here to my distribution. I'm going to create a new one. And this one's easy enough for me to remember what the mean is, right? 98.6 degrees is the mean. Okay, and the standard deviation, what did I say the standard deviation was? 0.6. Okay, point is equal to 0.6 degrees, 0.6 degrees. Okay, so now I want to know what percentage of the population is between 98 degrees and 99 degrees. Was that actually what the question was? Mm-hmm. Yeah, okay, good. So how are we going to figure this out using the table that we have here? Well, if I think about it, first thing I can do is I can calculate what's the z-score for 98, what's the z-score for 99. Okay, let's do that. Z is equal to 98.6 minus 98. I did that backwards. 98 minus 98.6 divided by 0.06, and that's equal to 0.6 over excuse me, what did I do wrong here? Oh, I'm sorry, this is 0.60. Okay, over 0.6 is equal to -1, and the z-score above is equal to 99 minus the x value minus the mean, 98.6, over 0.6, and that's equal to 0.4, right? Is equal to 0.4 over 0.6, which is equal to 0.67. Okay, so my z-score on this side is -1. My z-score on this side is equal to plus 0.67. Okay, so let's figure out how I'm going to do this. Now, my table, the one I use, the particular table I'm using, only gives me areas to the right of the z-score. So I'm not going to fight it. I'm going to actually take advantage of that. If I look at a z-score of plus 0.67 and look up the area that's represented by that in my table, then I know that it'll give me the area from here on down for this entire population. And if I look up the z-score of -1, it'll give me the area from z-score of -1 down below. So if I take the first area and subtract, which is this, and subtract the second area, which is this, it leaves me the area that I'm interested in between the two. Okay, so let's look it up. What is the area that's represented by z-score of plus 0.67 in this case? Let's see. Let me find it. Plus 0.67, 0.6. Well, the third significant digit, I have to go 0, 1, 2, 3, 4, 5, 6, 7, 7486. So that area is equal to 0.7486 out of 1, of course. And the area for negative 1, well, it's going to have to go to the other table. Right? The area for negative 1 is going to be equal to 0.1587. Okay, 0.1587. So I'm going to subtract this area, didn't really look proportional here, from the area here. Okay, so what does that come out to? It's going to come out to 7, 6. It's going to be 9, 3, 17. Not exactly new math, right? 9, 6, 13, 8. I know they do this completely differently in schools nowadays. It looks like it comes out to be roughly 59%. Okay, so 59% of the population has a temperature, will have a normal temperature between 98 degrees and 99 degrees. Okay, so, and you can calculate what percentage above that and below that and so on and so forth, but you can use this in all sorts of different ways. Just as long as you're flexible, and it helps, I think it helps, if you actually draw the distribution. You can avoid a lot of errors by drawing the distributions. You actually see what areas that you're working with. Is that working okay back there? Okay, good. All right, so yeah, you guys got, okay. Okay, 0.0, let's see, 0.00, oh yeah, that's the previous answer. Okay, good. Just looking at the answers online. Okay, so now, I can use this another way too. What if I were to ask you, what temperature represents the highest 10% of the temperatures in this population? Well, in that case, what I'm looking at is a situation like this. I'll redraw this. Okay, here's the mean, was 98.6, and sigma is equal to 0.6. Okay, so now degrees. Okay, so now what temperature is the warmest 10% of this population, a normal temperature? Well, what I'm looking for is the people that represent the top 10%, meaning that 90% of this distribution is below their temperature. 90% of this population is below their temperature. So I want to know what the value is that represents an area in the top 10% of this population's distribution. So now I know the area, but I don't know what the value of X is, right? But remember that formula we had before? The z-score for X is going to be equal to X minus the mean over the standard deviation. I know the mean, I know the standard deviation, and I'm about to know Z. How do I know what Z is? I know Z because I can go to the table and I can use it in the reverse. I can go to this table and I can say to myself, what z-score represents, remember, all these things in here are areas of the probabilities or areas of the normal distribution. What z-score represents 90% to the left? Okay, so I know it's not going to be the first part of this table, right? Because they're all below 50% because they're to the left of the mean. So if I go in here, let's see, 89, 89, 89.8. So it looks like it's right here. It looks like the z-score 1.2, was that 8? 1.28 is the closest to that. So that z-score represents 1.28. So I'll go back here. So 1.28 is equal to X minus the mean, which is 98.6, divided by the standard deviation, which is 0.6. Okay, now you know you can cross multiply here, right? So you can say that 1.28 times 0.6 is equal to 1 times x minus 98.6. So if I multiply this out, see if you guys can do it ahead of me. Okay, so 1.28 times 0.6 is that. I'm going to put that into memory. Okay, and then I'm going to take is that. So then I'm going to bring 98.6 over to the other side. It's going to become positive, so I can add it plus 98.6. So x is going to be equal to 99.37 degrees Fahrenheit. So that's pretty powerful, right? That you can do stuff like this with normal distribution. Okay, you guys, yeah, guys online got the same answer that I did. Good, that's reassuring. Okay, so you can actually use this to go the reverse direction as well. So I'm gonna move on from that slightly, and let's see, z table. Okay, normal distribution. I just want to show you how we would do this in Excel as well. Okay. I'm also going to point out to you a little why that empirical formula is a small lie. Okay, let's see. I'm going to open Excel. Okay, let me blow this up. Okay, so if I want to deal with calculating the normal distribution or standard normal distribution, I can use functions already built into Excel. For instance, I'll actually give you a list of these, or maybe a spreadsheet with a list of these. I don't think I put it up so far, but I do have it. Okay, so there are functions built into Excel. There's a function, for instance, norm s dist, and I'm going to put a parentheses around here. Notice that what it leaves open when I put the parentheses in, it recognizes the function and tells me it's waiting for the z-score, right? So let's say that the z-score, what was one of the z-scores we were working with before? Working with the number -1, for instance. So I'm going to put -1 in there, a z-score of -1, and hit enter. And it gives me 0.1586. That's the area to the left of that z-score. So if I gave it equal norm s dist, parentheses, if I set a z-score of +2, remember +2 is very close to 95%, 95% +2 -2. So if 95% is in the middle, that means that there's 2.5% in the tail at the top and 2.5% at the tail at the bottom. So I should see a number around 97.5, 95 plus what's in the lower tail for what's below this z-score. And indeed, 97, I actually get 97.72 because the empirical formula is an estimate. This is more precise than the empirical formula. Okay, if I put in 0 equals norm s dist, what do you expect me to get? 0, z-score 0 is the mean. So I get 50%. Okay, so now there's another function here, norm dist, not standard distribution, but norm dist. I'm going to put in parentheses. Oops, I left an equal sign out. I'm going to put in the parentheses, and it comes up with a greater number of different values. It wants to know the value of x, the mean, and the standard deviation, and something called cumulative. It's always going to be cumulative. Cumulative means it's adding the area from the left to the right. So it's just like the table we used so far, which is measuring the area to the left of whatever that value x is. So I'm gonna put in one of the problems we had before was we were looking at, for instance, let's see. Let me go back here and look at. We're looking at the area that represented less than 60 inches with a mean of 63 and a standard deviation of 3. So the mean, what did it want again? It wanted the x value, which was 60 inches, comma, the mean, which was 66 inches, comma, the standard deviation, which was 3 inches, comma, whether or not it's cumulative or not. Trust me, it's going to be true all the time for this function. Okay, I'm going to hit enter, and it gives me an area of 2.3% or 0.0227. Okay, so I can use norm S dist if I just want to convert the z-score into a probability, an area. I can use norm dist if I want to actually do a calculation where I know the mean and the standard deviation. I want to find the area, the probability represented with a specific value for x. I can also do the opposite. Like, for instance, the problem that we just solved with the area, okay, equals, this time I'm going to say norm S inverse, parentheses. Now, in this case, it's asking me for the probability. So if I know the z-score, right, if I know what the probability is, let's see what it'll give me. Remember, we're looking at this problem where we want to know when we're looking at the top 10%? Well, the area to the left of that would be 90%. So I'm going to put in 0.9. And let's see what it returns. It returns the z-score for me. Right? So norm S inverse. And I'll summarize this all for you. So the point here is that in addition to using that table or manipulating that table, you can also use Excel, all these functions in Excel that are available. There are others as well, but I will summarize them for you, and you'll have a few problems on the homework and so on and so forth. When you take the test, it will be up to you to use whichever one you want. You could use the table, or you can use Excel. Okay, that'll be up to you. I encourage you to if like I know a lot of you guys for some reason are allergic to Excel. It's like like you get hives when you see a spreadsheet, but it's really a valuable tool. It makes these calculations easy. For instance, when we use norm dist, I just had to put in x and the mean and so on and so forth, and put in all these values, and it gave me the value back immediately. Yes.
What's the difference between norm S dist and then just
norm S dist represents a function for the standard normal distribution. So if I put in a z, it's going to give me a percentage, right? But if I put in norm dist, it's actually something that's specific to your real. I notice it's asking for x and the mean, and so it's for your specific distribution. Norm S dist or norm S inverse is for all distributions. So it'll only work with a p-value. It'll only give you a p-value, which is an area, or it'll give you a z-score. This will actually give you'll be able to actually work with the number. So for instance, if you wanted to use norm S dist, you knew the mean, the standard deviation, so on and so forth, you want to use norm S dist, you would have to calculate the z-score and use it in there, for instance, right? So this one you avoid calculating the z-score because it does it for you and throws back the probability. Okay, so I'm going to move on at this point to, let's see what else we got here. Okay, right tail, left tail probability. Okay, higher value, no, it's this. 68%. Okay, what we you'll see some of these other examples that are in here. They actually you can actually, and as I said, I'll give you a summary of all these. But it's actually an exercise in actually typing in the function and seeing and using it to solve these other versions of these problems. Okay, so you can actually go through those if you want later on, but I'll give you kind of a summary sheet also. Okay, body mass index, here's another example. What proportion is overweight? The U.S. population, the mean of 25 kilograms per meter squared. What is that? Something's wrong there, right? The U.S. population has a mean of, is that BMI? Is that units for BMI? Could be. That could be that could be the actual units for BMI, right? Okay, it has a mean BMI of 25 and a standard deviation of 5, and is normally distributed. What proportion what proportion is overweight? In other words, a probability that people are greater than did I say here? proportion is overweight, has a BMI greater than 25 and less than 30. So you can find the proportion that's the proportion of population has a BMI less than 30, subtract the proportion of population has a BMI less than 25, and the difference is the proportion that's between 25 and 30, BMI 25 and 30. Just another notation, another way of giving a notation for this. Okay, I want to move on because for two reasons. One is I don't have my charger with me and my battery's going to run out. And the other one is I want to get into the binomial distribution. We'll make sure that we cover that because that was a little bit confusing before. Okay, so you can read through this, and really it actually works through each individual problem for you. So the answers are right there. Yeah, there you go, 99.37. Okay. What's that? Oh, excellent. Perfect. Terrific. Now a little bit of the pressure's off here. Terrific. I keep forgetting that actually there's other people beside, when you work in business, nobody has a Mac. Yeah. You're the only one with a Mac. But when you're at schools, there's a lot of them around. I keep forgetting that. Okay. Terrific. I hope it's got the right. Okay. Yeah. Uh-oh. No, am I wrong? I'm not sure it does. No, it's the wrong connector. This is the old style connector, I think, right? Yeah. Yeah, I got the pneumatic connector. So I even have adapters, but I don't have them with me. Got to bring them with me. There you go. Thank you anyway. Okay. So let's talk about the binomial distribution. Now, you guys remember, actually, I can take time pressure off. I can switch to the PC if I need to. You guys remember we had an example where we talked about probabilities, particularly probabilities that go one way or another. In other words, the probability that you would get a question right is 60%. Or the probability someone's diabetic is 10%. Or the probability somebody's nearsighted or left-handed is 30%, right? 0.3, they're either left-handed or they're not left-handed. Okay, so one of the examples that we gave was a coin toss. Really simple one. It's an easy one because it's 50%. Could be 50% chance of getting heads or tails. Doesn't matter. And the way we described the different outcomes that you could have was that we drew a probability tree, something that looked like this. In other words, probability that first toss was heads was 0.5, and the probability second toss was heads was 0.5. So we could actually multiply this out, and we could go out and make this probability tree even bigger. And so we could see all the different outcomes, and we could add them all together. And we could, at the end, say, if I toss a coin 5 times, what's the probability that I would get exactly 2 heads? And what's the probability I would get exactly 1 head? And so we could use the probability tree to do that. One of the ways that I can simulate this is, and I'm going to get this out of the way. One of the ways I can simulate this, imagine you guys ever see a pachinko machine? It's like a Japanese version of pinball, right? They have a whole bunch of little pins and it bounces around, does all kinds of interesting things. A little bit different than a pinball machine. But let's say that I had a pin right here. And I were to drop a steel ball straight down at this pin. It's got to go one way or the other. It's got to go left or it's got to go right. So let's say I'm pretty good at dropping it right on that pin. There's a 50% chance it could go right and a 50% chance it could go left. Let's say right below that, I put another pin so that that ball now hits this pin, bounces to the left. It could hit this pin and go to the left or to the right. It could hit this pin, go to the left or to the right, and so on and so forth. And then another pin and another pin so that as we come down, you get more and more different possibilities. So if I do this over and over and over again, this pin's all the way down, right? Where would I expect most of the balls to land? Where do you think? Well, each one of these is kind of like a coin toss. It could go to the left or to the right. So if there's 10 layers here, that's like tossing 10 coins. So how many heads would you expect to get? 5, right? So you would expect this ball to make 5 left turns, 5 left right turns. Might be 3 in a row, left and then two right. But you would expect the most common outcome would be an even number of left turns and right turns if it were really a fair machine, right? So most of the balls you would expect to see land in the middle, right? So what about as we got further and further, instead of 10, 5 left turns, 5 right turns, the next most likely outcome would be 4 left turns or 4 right turns, right? Or 6 right turns, six of left turns or right turns. So you would expect these balls to pile up in the middle, but the least number of balls is going to be the furthest out. So this is going to form a distribution, which kind of looks like this. What does that distribution look like? Looks like a normal distribution. It's not a normal distribution because it's not a normal distribution of, say, specific weights or BMIs for a population. It's a probability distribution for how many left turns, how many right turns. It's a binomial distribution. We can look at it as being almost like a normal distribution. In fact, Levi did. He told you that, if you look at what the probability is, right? Like for this is 0.5. And you look at what's the most likely the most likely outcome, the number of trials, the number of pins it's going to hit, that's 10, right? You could say to yourself, I could say that the mean number of left turns and right turns is going to be equal to n times p, or 0.5 times 1. So my mean number of successes, right, left turns, let's say, is going to be 5. That's going to be like my mean. That's the middle, right? 5 left turns would put me right in the middle. Okay. Now, what about my spread? My standard deviation could be equal to the square root of, now I'm going to get this wrong, right? It's going to be equal to p times 1 minus p over n, right? That's going to represent my standard deviation. So I can look at this two ways. I can actually calculate these probabilities using that really nasty formula. Let me find it here. I could either calculate this using that really nasty formula. See if I got it here. Nope. Let's see if I got it there. I don't have it handy, I don't think. Maybe I got it on my desktop. I don't see it. You remember the formula I'm talking about, right? That n times some p times p to the this power p to the x, n minus x, and so on. I can either calculate the actual probability, which is actually that's mathematically doing what the probability tree is doing. I'll calculate that, or I can make the assumption that's approximately a normal distribution. In other words, a normal approximation of the binomial distribution. I could calculate the probabilities that way. Well, I'm going to show you how to calculate the probabilities for real using Excel. Okay, and the way I'm going to do that is I'm going to go over here and I'm going to go back to our Word document there for our exercise. And I'm going to say, okay, but there is function in there, binom.dist. It's also binom dist. You could use either one. One's just been around a little bit longer. And we're going to take an example. A study indicates 10% of nursing home patients are diabetic. We're really playing that example out, right? You randomly sample 10 patients. Okay, what is your number of trials? There. First of all, what's your p-value, your probability of any particular patient being diabetic? 10%, right? What's your number of trials? You're going to sample 10 patients, right? Your trials, your n is 10 patients. Okay, so p, your probability is 10%, n, your sample size or your number of trials is 10. So now you want to figure out what the probability is for any of these outcomes. That exactly one will be diabetic. Okay, that 2 or less will be diabetic. Okay, so let's figure this out. So the way we would do this using the formula would be to plug in our n and our p, and our x would be 1, exactly one person. That would be our x. Okay, now I'm going to use Excel to do it. Equals, and I said, what was it, binom.dist? I could use .dist. I usually just use dist. .dist, put into parentheses, and it asks me, Number S, that's the number of trials. I'm sorry, that's the number of successes. Number underscore S is the first thing it's asking for. What's the number of successes we're looking at here? Exactly one. One. Okay? Comma, the number of trials. 10, right? With 10, which then randomly select 10 patients. Comma, the probability of any one of them being a success, being a diabetic. 0.1. Comma, cumulative. Cumulative means, I'm going to say false for now, and then I'll explain later on why I said it's false. False is going to give me just the probability for one person being diabetic. I'm going to hit enter. It comes out to be 38%. A little less, a little bit more, 39%. The probability, if you actually did this exercise and randomly selected these people, probability is 39%, 38.7%, that you would get exactly one person that's a diabetic out of 10. Okay, let's say I did it for 0. I'm going to put this over here. This is the number of successes. 0, 1. Let me see. Okay, I'll put a 0 there. I'm going to get this out of the way so I don't confuse myself. And I'm going to just center this. Okay, and this is 2, 3 successes, 4 successes, 5 successes, and so on. So what's the probability for 0 successes? Is equal to binom.dist, parentheses. Well, for 0 successes, the number of successes is 0, comma, trials is 10, comma, probability is 0.1 still, comma, false. This gives me the probability for exactly nobody out of those 10 people being diabetic. That's 34%. It's less likely than getting 1, but it's still pretty likely. How about, I'm going to do it now for 2, except I'm going to do a little trick here. Equals binom.dist, parentheses. Now for number of successes, instead of typing in the number 2, I'm going to actually give it that cell, B2. The number that's in B2, comma, the number of trials is 10, comma, the probability of success is 0.1, comma, false, and hit enter. And it's 34%. Oh, look, it's symmetrical with that 0. Okay, now I'm going to also go here 6, 7, 8, 9, 10. So now if I copy this down, the formula will get copied down, and it will calculate the probability. Oops. Let me see what I did wrong there. Okay, is equal to, oh, B2 is wrong. It's this. There we go. Okay, it's 19%. That's better. It makes more sense. Okay, and I'm going to copy that down. I hope I didn't confuse you guys by getting that wrong. And notice that the probability of getting 3 people out of 10 when I randomly select patients from this population is only 6%. 5 people, half the people, is almost 1 in 1,000. Not very likely because the prevalence is only 10%, right? And then 10 out of 10 is like hitting the lottery, right? It's like 1 in a million, 1 in more than a million, right? So very unlikely I would get 10 out of 10 in this situation, right? So now, but this represents all of the possibilities for this binomial distribution. What do you think I'm going to get if I add up all these probabilities? Bingo. There you go. Exactly right. See, you didn't need me. You could have figured this out all on yourself. I'm going to show you something very interesting. What's the probability? How would I figure out what the probability of getting 2 or fewer diabetics in this population? How would I figure that out? Well, the probability of getting 2 is this. Probability of getting 2 is this. Probability of getting 0 is this. Well, it's the sum of those 3, right? Because 2 or less would represent the sum of the probability of getting 2, the probability of getting 1, the probability of getting 0. So the probability of getting 2 or fewer is 93%, right? That's 2, 1. I'm going to show you something else interesting here. Remember we looked at that formula? Binom.dist, parentheses. And I'm going to go in here this time, and I'm going to say to myself, the number of successes is equal to 2, comma, trials is 10, just as I did before for 2, comma, probability is 0.1, comma, cumulative, this time I'm going to say true instead of false. And if I hit enter, It gives me the sum for all of the possibilities from that value number of successes on down. That's what cumulative true or false does for you.
Just for that value.
Just for that value. Exactly. So instead of like adding up those different probabilities, you could just use true there instead of false. If you want, if I asked you what's the probability of getting more than 2 people that are diabetic if you sample 10 people in this population randomly? What's the probability for getting more than 2? Well, the probability for getting 2 or fewer is 0.928. The probability of getting more than 2 is equal to 1 minus 0.928. Okay. Now listen to the words here. Listen to the syntax here. What's the probability of getting 4 or more diabetics in this when I sample this population? 4 or more is the same thing as 1 minus 3 or less. Right? If I had said more than 4, it would have been 5, 6, 7, 8, 9, 10. If I say 4 or more, then it means 1 minus 3, 2, 1, or 0, probability 3, 2, 1, or 0. Right? So if I wanted to know that, I would say the probability is equal to 1 minus binom dist, parentheses. Notice I didn't bother with period this time. And the number of successes is going to be 3 for 4 or more, comma, trials is 10, comma, 0.1, comma, and true, right? Because I'm going to subtract. This is the probability cumulatively for 3, 2, and 1, and 0. And the probability is only about 1% for 4 or more. Let me see if that's really 2. Equals the sum of 4 or more. Whoops. I did wrong. Sum of these values. There, it comes out to the same thing, right? So it works, genuinely works. I just want to show you another thing. I just show you that I didn't make this stuff up, that this stuff really does work. Hang on a second. Okay. This is a exhibit at the Queen's Museum of Science. Something called a Galten machine. This is when I was a little bit more ambitious and actually put, this is a machine that does exactly what I was describing to you, right? And kids are just standing in front of this thing watching these balls comes down. Now watch, it hits the pin, can go to left to the right, left to the right, left to the right, left to the right, so on and so forth. And then the balls accumulate down at the bottom. Okay, so come down here, you get to see the bottom. There's an outline of a normal approximation to the binomial distribution. There they go. Magic, right? Is that cool? Right, and if you wait there long enough, you'll see it really does. The more larger your sample sizes, the more balls you drop down to the closer to a binomial approximation, normal distribution to actually get. So if you get a chance, a lot of interesting exhibits at the Queen's at the New York Science Museum, which is at the old World's Fairgrounds in Queens. I think it used to be the Queen's Museum. Not sure. Okay. So at any rate, you know, I'm thinking that with me running out of battery, I'm trying. Oh, you know, I wanted to go over one more thing. Remember what we were looking at before with that probability during the Levi's lecture. So I want to open that up. Okay, let's see. Okay, I think, nope, that's not it. Where'd it go? Normal distribution. Oh yeah, that was just that. I'm gonna put this back here. Shouldn't have been B11. Yeah, you're right. Somebody caught me on that error. I wish I had looked at that before I actually did it. Standard normal distribution tables. Where did I put it? You know, it's on the desktop. I know where it is. Okay, date modified. Other way around. No, it should be there. Venn. I think it was that Venn diagram. There it is. Okay, remember this slide that we were just looking at before? Okay, I want to discuss this slide. Okay, so now let's say notebook. Okay, let's say I'm looking at this slide, and let's say that the probability of having cancer is 10%. Probability of having heart disease is 20% in this population. Okay, let's assume for the moment they're not mutually exclusive, but that they're independent. In other words, there's no relationship. Having heart disease makes you no more likely than the rest of the population to have cancer, and vice versa. Okay, so now let's take a look at this Venn diagram. In this Venn diagram, we have cancer, and we have heart disease. I made the heart disease one a little bit bigger because it's a little bit more likely, and everybody else is outside of this. So the probability of having cancer is 10%. Probability of having heart disease is 20%. So I'm going to draw a contingency table, and I'm going to take 100 people, right? And this is going to be cancer or no cancer, right? And this is going to be heart disease or no heart disease. Okay, and I'm going to divide this up. I'm going to say to myself, okay, so what in this population, what's the probability of having cancer? Is 10%, right? So how many people have cancer? 10 out of 100. 90 people don't have it. Okay. So what's the probability of having heart disease? 20%. So out of these 10 people, 2 of them are going to have cancer. 8 of them are not going to have cancer. That's probably the way that this will shake out. Same thing, 90%. 90 people, probability is 20%. This would be 18 people. This would be 72 people. So I got 20 people that have heart disease, and I have 80 people who don't. And that matches up with the prevalence for heart disease, right? 20 out of 100 have heart disease. Okay, so let's take a look at our formulas here. First formula is the probability, probability of union of having cancer and having heart disease. That means you have either heart disease, or you have cancer, or you have both. Is equal to the probability you have cancer plus the probability you have heart disease minus the probability that you have both. Well, if I look at this, the probability you have both is this area in here. The reason why you have to subtract that, the reason why you have to subtract that, I'm gonna run out of power. You know, I'm going to do this online because I don't want to lose the recording. And guys, I'll record this online and post it later on tonight. And I'm going to break at this point because I don't want to screw up the recording in the background. And so watch for it online. By the way, I'm going to send out a note to see if there's anybody objects to on Wednesday doing the lab first, so you can as an experiment, and then having you look at the lecture afterwards. In other words, starting the lab at 5:30 instead of later on, because I think maybe it'll help you understand how the rest of this stuff works.
Hi, Mom. Oh, I'm so happy to see you. Just to be clear, my girlfriend and I aren't just vegan, we're raw vegan, which means no meat, no dairy, and absolutely nothing cooked at all. Thank you. Mom, come back soon, okay? Monica's making some nutmeg soy butter. Oh, how wonderful. Thank you.
Chang, that was my daughter, and she obviously did not